Today we're going to study Ptolemy's theorem that applies for a cyclic quadrilateral with sides A, B, C, D, and diagonals E and F. The theorem states that in all such quadrilaterals, AC plus BD equals EF. To prove this, let's first label the angles in this quadrilateral. Let's call this angle alpha, this angle gamma, and this angle beta. Then, because of the sum of the angles in this triangle, we know that this angle is 180 minus alpha minus beta minus gamma. Since this is a cyclic quadrilateral, we know that if this angle is gamma, then this angle is gamma. They both correspond to this arc of the circle. And if this angle is beta, then this angle is beta. And if this angle is alpha, then this angle is alpha. And also, if this angle is 180 minus alpha minus beta minus gamma, it corresponds to this arc, so it equals this angle, 180 minus alpha minus beta minus gamma. Now we can apply the law of sines. If big R is the radius of this circle, then we know that A equals 2 times R sine of alpha, B equals 2 times R sine of beta, C equals 2 times R sine of gamma, D equals 2 times R sine of 180 minus alpha minus beta minus gamma, E equals 2 times R sine of alpha plus beta, F equals 2 times R sine of beta plus gamma. Now we can take the expression AC plus BD minus EF and replace each of the letters with the corresponding 2R times the sine. And this is how we get this expression here, from which we can take 4R squared in front, and in the parentheses, we get sine alpha times sine of gamma, sine of beta here, times sine of 180 minus alpha minus beta minus gamma. This sine equals just sine of alpha plus beta plus gamma, so we put it here, and then minus sine of alpha plus beta times sine of beta plus gamma. And we should prove that this expression equals 0. Now let's group the alpha plus beta in the alpha plus beta plus gamma, and apply the formula for sine of one angle alpha plus beta plus another angle gamma. We get sine alpha sine gamma is here, plus sine beta times sine of alpha plus beta cosine gamma, which appears here, and then sine beta times cosine alpha plus beta sine gamma, which appears here. And then minus, we apply the formula for sine of beta plus gamma, so we get sine of alpha plus beta sine beta cosine gamma, which is here, and sine alpha plus beta cosine beta sine gamma, which is here. And now you can see how this term cancels out with this term, and also all the other terms have sine of gamma, so we can take sine of gamma in front. And now we get 4R squared sine of gamma in front, and then into parentheses sine of alpha here, sine beta cosine alpha plus beta here, and sine alpha plus beta cosine beta with a minus sign here. And now notice that sine times cosine minus cosine times sine of the same angles, this is a formula. This represents sine of beta minus, and in parentheses, alpha plus beta. And so we get this expression here. Sine alpha comes from here, and then this expression turns into the formula sine of beta minus alpha plus beta. But sine of beta minus alpha plus beta, this is sine of minus alpha. And sine of minus alpha equals minus sine of alpha. And therefore it would cancel out with the sine of alpha here. And the whole thing would become 0, which is what we had to prove, that AC plus BD minus EF equals 0, which means that AC plus BD equals EF. Now we're going to prove two theorems that relate to the quadrilateral in the general case, so it's not necessary that the quadrilateral be cyclic for these two theorems to be true. The first one is called Ptolemy's inequality. You see that for cyclic quadrilaterals, we have that AC plus BD equals EF, and for non-cyclic quadrilaterals, then AC plus BD is always greater than EF. And the second theorem that we're going to prove is called Bretschneider's theorem, and it states that for all quadrilaterals, a squared c squared plus b squared d squared minus 2 times abcd cosine of alpha plus gamma equals e squared f squared, where a, b, c, and d are the sides of the quadrilateral, e and f are the diagonals, and alpha and gamma are, for example, this angle and this angle, a pair of opposite angles in the quadrilateral. Of course, you can notice that Bretschneider's theorem is a generalization of Ptolemy's theorem, since for cyclic quadrilaterals we know that alpha plus gamma always equals 180 degrees, so this cosine would be 180 degrees, and cosine of 180 degrees is -1, so this minus is going to become plus, and we're going to have a squared c squared plus b squared d squared plus 2 times abcd, which equals AC plus BD squared. Hence, for cyclic quadrilaterals, we would have AC plus BD squared equals E squared F squared, and therefore AC plus BD equals EF. And now let's focus on proving these two statements. Suppose this is our quadrilateral with diagonals E and F, angles alpha and gamma here and here. I'm going to construct two triangles, one here and one here. And these triangles would be such that this triangle is similar to this triangle. As you can see, this angle equals this angle, and this angle equals this angle. And I'm going to construct this triangle such that it is similar to this triangle here. As you can see, this angle equals this angle, and this angle equals this angle. Similar triangles have proportional sides. Therefore, this side divided by this side equals this side divided by this side. And so, if this is A, this is B, and this is E, then we have this side divided by A equals B divided by E. And so this side must be A times B divided by E. Similarly, we have that this side divided by this side equals this side divided by this side. And so this side divided by A equals C divided by E, and therefore this side is AC divided by E. Similarly, we have that this divided by this equals this divided by this. And so this side must be AB divided by E, and this side divided by this side equals this side divided by this side. And therefore this one is B times D divided by E. Now notice that this segment equals this segment. And now we're going to prove that this segment is actually parallel to this segment here. From this triangle, we know that the sum of this angle, this angle, this angle, and this angle is 180 degrees. But you see that this angle moves here, and this angle moves here. And therefore the sum of this angle, this angle, this angle, and this angle is 180 degrees, which means that the sum of this angle and this angle is 180 degrees, meaning that this line is parallel to this line. Hence, these two segments are equal and parallel, and therefore the quadrilateral they define is a parallelogram, which means that if this length is f, then this length here is also f. And now to prove Ptolemy's inequality, we just need to apply the triangle inequality for this triangle here. We have that this side plus this side is greater than this side, so AC divided by E plus BD divided by E is greater than F, and hence AC plus BD is greater than EF as desired. Note that this angle equals this angle, and this angle equals this angle, and the sum of these two angles is alpha, and therefore the sum of this angle and this angle is alpha, so this whole angle here is alpha plus gamma, meaning that this angle is 360 minus alpha minus gamma. Now suppose what would happen if that quadrilateral was cyclic. Then alpha plus gamma would be 180 degrees, and this angle would be 180 degrees, meaning that this point, and this point lie on a straight line, in which case we would have AC plus BD equals EF. But if the quadrilateral is not cyclic, then this angle is definitely not 180 degrees, meaning that these 3 points define a triangle, and for this triangle we can apply the triangle inequality and get that AC plus BD is always greater than EF. Now let's apply the law of cosines for this triangle here. We get that F squared equals AC over E squared plus BD over E squared minus 2 times AC over E times BD over E times the cosine of this angle, so cosine of 360 minus alpha minus gamma, which is written here. How do we transform cosine of 360 minus alpha minus gamma? Well, let's turn to the unit circle here. If this angle here is alpha plus gamma, and we take this angle here to also be alpha plus gamma, then this point would correspond to the angle alpha plus gamma, and this point would correspond to the angle 360 minus alpha minus gamma. And so cosine of 360 minus alpha minus gamma would be the cosine corresponding to this point, which is this red length here, which is exactly the same as the cosine corresponding to this point, so the cosine of the angle alpha plus gamma. And so cosine of 360 minus alpha minus gamma equals cosine of alpha plus gamma. Now we take this equality, we replace cosine of 360 minus alpha minus gamma with cosine of alpha plus gamma, and we multiply both sides by e squared. Then we get e squared f squared on the left-hand side, and on the right-hand side we get a squared c squared plus b squared d squared minus 2 times abcd times the cosine of alpha plus gamma, which is exactly what we needed to prove. This is called Bretschneider's theorem for the quadrilateral. This is the optional problem. We have an equilateral triangle, and this here is its circumcircle. A random point is chosen on this arc of the circumcircle, and this distance here is a, this distance is b, and this distance is c. We need to prove that a plus b equals c, and here's the solution. Let the side of the equilateral triangle be equal to x. Then we can apply Ptolemy's theorem for this cyclic quadrilateral, and then we get a times x plus b times x equals c times x, as written here. And now we can cancel out the three x's, and we get a plus b equals c as desired.